Okay, guys, welcome. Today we're going to talk about bipartite graphs. Okay, now the motivation for these types of graphs is that we're going to suppose that 300 students take part in a dance, and they don't all know each other, but we have that every girl knows exactly 50 boys, and every boy knows exactly 50 girls. And of course, we'll assume that acquaintance is mutual. Now, we claim that all students can all dance simultaneously so that only pairs who know each other dance with each other, right? So we don't have any sort of intermingling of girls and boys that don't know each other, right? Now, of course, this situation is natural to describe with a graph. Now, what we want to do a little bit differently this time is we want to arrange the nodes so that the nodes on the left represent boys and that the nodes on the right represent girls. Right? So maybe something like this, and we want to connect every node on the left with a node that's on the right. Now, this type of graph is called a bipartite graph, and we are looking for what's called a perfect matching, right? Where we can join each one of these. Now, they're bold here, but just to indicate a little bit more clearly, the perfect matching is going to be indicated by these dark black edges here. Right, and they're formed only from the original edges of the graph, right? Now, to be a little bit more precise, we say that a graph is bipartite if its nodes can be partitioned into two classes, say A and B, such that every edge connects a node in A to a node in B. And of course, a perfect matching is a set of edges such that every node is matched with exactly one of these edges. Right? So in other words, our current problem is now restated in graph theory language as we have a bipartite graph with 300 nodes, each with degree 50. We want to show that it contains a perfect matching. And it turns out that the following theorem exists for this. We have that if every node of a bipartite graph has the same degree d greater than or equal to 1, then it contains a perfect matching. Okay? And this is something that we'll prove later. But we have that if every node of a bipartite graph has the same degree and that degree is bigger than or equal to 1, then it contains perfect matching. So of course, in our scenario, every node has degree 50. So of course, we're going to have a perfect matching there. Now, for a bipartite graph to contain a perfect matching, it's necessary that the number of nodes of A is the same as the number of nodes in B, of course. Now, if every node has the same degree, then of course we're going to show that this is true. Well, let's suppose that every degree for all these nodes is D, right? And of course, in our case, that was 50, but in the general case, we're going to assume that it's D. Now, the number of edges is the number of nodes times the degree of each node, so D times the size of A. But of course, that's also the same as D times B, right? So then from that, we would divide both sides by D. And of course, that would necessarily imply that A is equal to B. Okay, now let's look at another motivating example. We're going to suppose that an island is inhabited by 6 tribes, and they agree to split up the island so that each tribe has 100 square miles on the 600 square mile island. Now, tribes decide to pick new totems, and that each should pick one of the 6 species of tortoise that are on the island. They each need different totems of each and corresponding tortoise. Each of these should be somewhere in their territory, right? So, for example, oh, and the other thing, of course, is that the tortoise habitats are also 100 square miles, but they don't overlap. Now, these regions that are separated by these solid lines here are the tribe regions. Right, so we have something like this. Right, and that separates the island into each of these regions where the tribes live. Now, these dotted lines, which I'll do in orange, are where the species of tortoise live. So now to make these totems, each tribe is going to select a species of tortoise that lives in their tribe's region, right? And of course, we want to prove that this is possible. So we're going to use a graph for this situation. We're going to represent the tribes with a node as well as the tortoises by node. And of course, we'll have in one class of our nodes, we'll have the tribes, and the other class will have the species of tortoise. And we're going to connect the tribes to tortoise species that are on their territory. So we have a bipartite graph, and we want to find that there's a perfect matching, right? So here's all of our tribes, and here's our tortoises, right? And we've connected tribes to tortoise if that species of tortoise is on that tribe's prescribed land. Now, this is similar to our other problem, except the difference is that now these nodes do not all have the same degree, right? Some have 3, some have 2, one even has 4. All right, so we want to see how we can get a perfect match. Now, in this setting, we could generalize this to say that the combined territory of any K tribes would hold at least K species of tortoise, right? So this means for any value of K, if we have K nodes on the left, there should be at least K nodes on the right connected to at least one of them. And of course, we'll see that this is all we need, right? And this is going to rear its head in the idea of the marriage theorem, okay? So the marriage theorem says that a bipartite graph has a perfect matching if and only if the size of the set of nodes of A is the same as the size of the set of nodes in B. And for any subset of K nodes of A, there are at least K nodes of B that are connected to at least one of them. Okay. Now, before we prove this, just note that if we switch left and right side sets of nodes, we would still have the perfect matching, right? Because the left and the right sort of has no indication, right, if we did right or left to right, right? So they sort of hold the same properties. Okay. Now, to prove this, we're going to consider the conditions of the theorem A equals B, and for any subset of K nodes, there are at least K nodes of B that are connected to at least one of them. We're going to call this just a good graph, right? Just for convenience, okay? Now, hopefully it's obvious that every graph with a perfect matching is good, right? Because, of course, any graph that has a perfect matching, right? So something like this, there are at least K nodes of B that are connected to at least one of the nodes on the left, right? So if you pick these K nodes, there's at least K, or in this case, there's at least 4 that are connected to them. And of course, that holds true, right? So now we just need to show that every good graph contains a perfect matching, right? So we're going to consider a graph with just 2 nodes. Being good nodes means that these are connected, okay? Now, to be a perfect matching, a given graph must be able to be partitioned into good graphs with 2 nodes, right? So we want to divide the nodes into classes and keep the edge between 2 nodes only if they are in the same class. So our plan is to partition the graph into 2 good parts, then partition each of these into 2 good parts, and keep repeating this until we are left with just a bunch of good parts with 2 nodes. Right? And of course, this has to be true because if we have that A is equal to B, we should be able to sort of do a 1-to-1 pairing from A and B, right? Of course, this will leave the edges that form a perfect matching. So now remember, what we want to show is that if a good bipartite graph has more than 2 nodes, then it can be partitioned into 2 good bipartite graphs. So we're going to select 2 nodes, A from big A and little b from big B. And they'll be connected by an edge, and let these nodes be the first part and the other nodes be the other part. Now, the first part, of course, is good based on our definition, but what about the second part? Now, it may have some set S of K nodes on the left connected to fewer than K nodes on the right, as shown by this diagram, right? Now, in the original graph, these K nodes were connected to at least K nodes, but if I take out this A and B of the first part, right, only holds if the kth node, right, if this kth node was B, then we would be fine. Okay, now we're going to let T denote this set of neighbors of S in the original graph, right? So of course we're going to let, in this case now, if that's S, this is now T. Okay, and of course these are the same size. Now if we try a different partition, we will take S union T together with the edges between them as one part and the rest as the other part, right? So now we're taking this region and this region, these three nodes and these three nodes, as one part, and then A, and then those other nodes as the rest. All right, so we sort of eliminated the possibility where we could potentially lose a node that we would need. Okay, now our claim is that both of these parts are good. Now, for the first part, take any subset of, say, J nodes in S. Since the original graph was good, they're connected to at least J nodes that are all in T, right? So we sort of ruled out that possibility. So if I pick any of these two, for example, they would be connected to at least two in the set T. So that part's good. For the second part, you would use the same argument as you did for the first part, but now just switch S and T, and then that would prove the result. All right. So that concludes this video on bipartite graphs. I hope you enjoyed, and I will see you next time.